Good morning, everyone. I trust last week's work went smoothly and that you're still able to check your answers in the textbook. If you're struggling with access to Active Teach for any reason, please can you let us know? Because we're sort of assuming that in the most cases you can check your own work. So just want to sort of review where we got to. So we've got this idea of some random variables can be modelled using the binomial distribution. So let's just say that I decide I'm going to play table tennis against Mr. Gobber. Mr. Gobber's he's fairly handy at table tennis, but the chance I beat him is still 0.6. Okay, so let's imagine we play 8 games. So we've got these 4 conditions that we need to be true for the binomial. Fixed number of trials, so we're only going to play 8 games. The probability, the game has a sort of success-fail criteria, so either I win or he wins. The probabilities don't change, they stay the same, and one game is independent of another. Now those last 2 you could argue are a little bit dodgy when you're playing someone 8 times at table tennis, because you do learn each other's strengths and weaknesses, but it's a model, isn't it? It's always going to be imperfect. So what I've done is I've worked out the individual probabilities. We can use our calculator to work those out. So this is the probability that I lose every game, very, very unlikely, obviously. This is the probability that I win every game, still relatively unlikely. You'll notice that the peak probability comes at around 5. So that's the highest probability. Remember, this is discrete, so I can only have a score of 0, 1, 2, 3, 4, 5. I can't get 3.5 wins. And the calculator would tell us those, but also we've got the manual way of doing it. So for example, the probability that I win 2 games, well, that's 2 wins and 6 losses, but that's not the only way it can happen. It's not just I win the first 2 and lose the 6. So this is the number of ways that can happen. So that's how you do that longhand. You will never need to do that, but I think it's worth having that sort of in your mind as to where the probabilities on the calculator come from. And of course, what we were doing in the second session was we were working out collections of probabilities. So we were getting our calculator to work out, say, the probability of getting 5 or more, or the probability of more than 3, and the calculator was adding those probabilities up for us, or the probability of scoring at least 2. It was things like that which were quite fiddly, weren't they? So there we go. Those are the probabilities for each of those situations. And I've plotted them on a graph. So here are those probabilities plotted on a graph. So we can only score between 0 and 8. And just a couple of things I want to point out. Firstly, the peak. I said the peak was at 5. We have this peak, this most likely value, is sometimes referred to as the expected value of x, so that's the notation we use for it. Sometimes it's referred to as the mean of x, and that's because if Mr. Gobber and I played each other 8 times, lots and lots of times, so we played each other 8 times on Monday, 8 times on Tuesday, 8 times on Wednesday, 8 times on Thursday, it is likely that me winning 5 times would be the average number of wins. And you can predict the expected value of x. It's always that number, which remember we call n, the number of times we do it, multiplied by that number. So E of x is n times p, which is, in this case, 8 times 0.6, which is 4.8. This is discrete data. You can't have 4.8 wins, so that's why 5 is our highest probability. Now that graph is often drawn in a slightly different way. It's drawn with a smooth curve, so these points are the heights of the bars. Now, it is very easy to criticise this. You could argue, well, this is bad maths, because by joining up those points, you're implying that you can have a value between 1 and 2, but you can't. We are saying that these are the number of games I win, and I can't win 1.5 games. But it's just a graphical representation. And do you remember last week I said, say you were asked to find the probability of 6 or more, I would draw a little picture just to make sure I've got that right in my head. So the probability of 6 or more would be that, and on my calculator I'd type in minimum 6, maximum 8, and it would work it out for me. Well, the other way of representing that is to say, okay, the probability of 6 or more is that. So this is an alternative way of representing that. It's just a tool that we use to visualize the problem. Okay, using this sort of approach, you're sort of basically saying the area under that graph is 1, because that's all the probabilities added together, and so we're looking at particular subsets of that. And that approach is useful in this next step, which I've called inverse binomial probabilities. Didn't make my second point about the graph, did I? So I said about the peak was predictable. E of x is equal to n times p. The other point about the graph is it's not symmetrical. So it's that sort of bell curve shape, which we're quite familiar with in statistics, but it's not symmetrical. And binomial probabilities are not symmetrical unless, well, I'll give you a, maybe that's a little puzzler to think about. What would have to be true? What would I have to see here in order to get a symmetrical binomial probability distribution? Okay, so moving on then. Well, I'm not moving on at all with this first two questions, actually. You should be able to answer this based on what we did last week. Okay, so I'm going to ask you just to pause the video at this point and just see if you can answer this question. Obviously, there's another bit to come, which is the new stuff, but see if you can just answer this question. It's just another example of what we did last week. Okay, so here are my answers. Here's my picture for the first one. No more than 2 means 0, 1 or 2, so it's like that. Or using my little sort of graph representation, it's that, isn't it? And at least 5, well, that's that, isn't it? And using my little graph notation, it's that. Now, how did I know that 5 was after the peak? Well, because I know that the peak is often referred to as the expected value of x, and that's n times p. So I know that this was going to be around 3 or 4, so that's after the peak. And of course, my answer confirms that, because it's less than a half. I know it must be after halfway through the graph. Remember, this is just another way of representing this, and it's just a little bit quicker perhaps than sort of drawing out the great long list. Okay, so let's move on to the next step. This is this inverse binomial thing I was talking about. So she wants to use this spinner for a competition, and 12 spins and the number of reds gets recorded and you win a prize. It doesn't make it very clear, but what you get a prize for is if you get a particular number of reds or more. She wants the probability of winning to be less than 0.05. So, these are all the possible scores, aren't they? And she wants the probability of winning to be less than 0.05. So let's say we work out that the chance you need 8 or more to win. What that means is that the probability of all of those has to be less than 0.05. That's a bit confusing, but look at my graph. That's perhaps a little bit easier, isn't it? We know that we can score between 0 and 12 in this game. We're spinning the spinner 12 times. We might get no reds, or we might get 12 reds. We want to know the value here, which remember has to be a whole number, which gives us a probability not of that value alone being 0.05, but of all the probabilities between that and 12 being 0.05 or less than 0.05. So I'm going to do this on my calculator using trial and error. So I'm going to go back here, and I've got my values already set in, 12 trials, probability 0.3. I'm going to keep the upper at 12. I know that 5 to 12 is 0.2763, because that's the answer to this question here. So I'm going to increase that to 6. What's the probability of 6 to 12? What if that's 6? What do we get as our probability? 0.017. So that's still more than 0.05. Okay. So let's go to 7 to 12. 0.03. That is less than 0.05. So this value here must be 7. So what we're saying is that the probability of getting 7 or more, all of those probabilities added together, is less than 0.05. So Jane needs to make the number of reds you need to win a prize 7. Okay, so 3 questions from page 94 in the textbook. First one I'm going to work through with you, and then I'd like to have a go at the other 2. I've put the questions on an attachment to class charts, along with the graphs that I spoke about a little while ago, and the example that we've just worked through. But I'm hoping that you've got, as I said at the beginning, textbook access, because you'll need it to check the answers. I'm going to go through this one with you anyway. So we're dealing here with a random variable. Don't find the focus. There we go. Random variable where we're doing something 50 times, and every time we do, the probability of success is 0.4. And I want to know the largest value of k such that the probability x is less than that is less than 0.05. There's a lot going on there. So let's draw a picture. I'm going to draw my graph picture. Now I know I said it's not symmetrical, but I'm just going to draw it symmetrically. Again, we're just a representation. We're just using it to help us understand the problem. So 0 is the lowest I can score, 50 is the highest I can score, and I want to know the value such of k such the probability x is less than k is less than 0.05. So I'm looking for a value here, so that this area here is less than 0.05. So this is my picture explaining what this means, because I think this is really confusing. X has got to be less than or equal to that value, and I want this to be less than 0.05. So I'm going to do this using trial and error on my calculator. I'm still in binomial cumulative distribution mode. There is an inverse binomial mode, but we found it last year with my group really hard to get your head around the way that works. So we found this trial and error approach worked better. If you want to have a go with the inverse binomial thing, that's brilliant. By all means do. Okay, so I want to know a probability between 0 and a particular value. So I've entered my 50 and 0.4, and I'm starting with 10. There you go. So I'm working out the probability from 0 to 10. So this time I fixed the lower at 0, and I'm working out what that value there is. Okay, that's still really small. I want 0.05, which is 5 times 10 to the minus 2. I've got a tiddly value there. So let's make it up to 15. Okay. So this is now bigger than 0.05. So I've gone too far. I want a value, I want the last value, which is less than this. So 15 is too far. So let's go down. I know it's between 10 and 15. Let's go down to 14. Right, 14 is just bigger. So that's no good. That's no good. All right. So it's probably going to be 13, isn't it? Let's just double check. Yeah, 13. If I make that 13, the probability here is 0.0280, 4 decimal places, or to 2 decimal places, 0.03. So it's less than 0.05. It can't be 14, because that gave me a probability that was greater than 0.05. So the answer to that first one is that k is 13. Second one, the smallest number r such that if x being bigger than r has a probability of less than 0.01. So now we're at the other end of the graph. 0, 50. I want a value here such that the probability here is less than 0.01. Now, you'll notice that it's greater than, not greater than or equal to. So I'm going to carry on doing my trial and error as I did for the previous one, and then we'll then just see what difference that makes when I get the answer. So let's try and find the value here that gives me a probability, the first value here that gives me a probability of less than 0.01. So here we go. Same two thing here, but now I'm fixing the upper at 50 and I'm changing the lower. So let's start with 40. That would be a good one to start with. Right. Tiny, absolutely tiny. Can you see how that's 0.80 is an 8? Okay, so I went too big. So let's go back to 30. Okay, so that's 0.003. It's less than that, but a lot less. So I need to go back a bit further. So let's go to 25. I'm moving this value back. 0.097. So I've gone too far now. So let's start winding it up. 26, 0.05, 27, 0.03. Remember, I wanted the first value that's less than that. 28, 0.016, bigger than this, but we're getting close, aren't we? 29. Right, that's smaller. That's 0.007. So 29 is the biggest value there, the first value there that gives you a probability of less than 0.01. We want to know the value that x has to be bigger than, so the answer here is that x has to be bigger than 28. 29 is the first value that gives us the probability we're after, but because we're asking what's the value that x has to be bigger than, it has to be bigger than 28. So have a go at 8 and 10 on that page, and tomorrow I will show you the answers. All the best.